welcome to our channel Euclid Mathematics. We have started lecture series on CSIR NET previous year question, GATE previous year question and other competitive previous year question. Within that, I already uploaded plenty of the videos on my channel. Now in my today's video, I'm gonna explain to you all one of the question. It is from the GATE exam. It is the latest question as GATE exam is coming. So you all need to be familiar with the previous year questions. So these questions are very much important. Okay, so if you wanted to see more videos like this, you may check it into my playlist. Already plenty of the videos I uploaded on my channel. Okay, so now in my today's video, I'm gonna explain to you all one of the previous year question from GATE exam. Okay, now here first of all I'm gonna explain to you all question and then we'll go for the detailed understanding of solution. Here our question, it is no answer type question, so we have to fill in this blank. So we have given V is a set of a solution. Okay, V is a set of all solution of equation y double dash plus ay dash plus by which is equal to 0, satisfying y of 0 which is equal to y of 1. Where a and b are positive real number, then we want the dimension of V. Okay, that means V is a set of all solutions. So we have given V is a complete set of solution, and the dimension of V, that means a set of solution means in our solution how many constants are present, that we call it as the solution of our V. Okay, so solution means if I have, for example, let me explain in some simple form what is meant by solution. So if x which is equal x square which is equal to 1, then x square minus 1 which is, if I have equation x square minus 1 which is equal to 0, then the set of solution for this x. Okay, so how many possible value for x is possible? Okay, how many values are there, that if we substitute these values over here, then we get this two sides equal. Okay, this is called the set of solutions. So here we have possible some constants. So for example, if I consider x is 1 in our equation, we get the 1 minus 1 which is equal to so 0 which is equal to 0. Okay, that means set of solution means our constant which satisfy our given equation. Okay, that means this is the solution of our equation. So we have given differential equation, double order differential equation. So we have to find out the solution of our differential equation like this. Okay, so here is the x is equal to 1 is one of the solution for our equation. Okay, so we have to find out similar solution for our differential equation. Okay, so this is the solution, set of solution which satisfy our equation. Okay, there are other solution to -1 iota, some other solutions are also there, but for your better understanding I explain this one. So we have to find out the solution for this differential equation using these two conditions. Okay, now let's find out the solution. So in the part of a solution, I consider over here our differential equation y double dash plus ay dash plus by which is equal to 0. Okay, this is our differential equation. By using this one, find out the quadratic equation and then find out the root, and we'll go for finding the solution. Okay, so y double dash we compare it with the d square y. Okay, so it comes as a d square y plus a into d plus b completely y which is equal to 0. Okay, so this is the way to compare our differential equation with the quadratic equation. Okay, so I got the some type of a quadratic equation over here. By using this quadratic equation, we have to find out the value for d. Okay, so let's find out the value for d. We'll see what is the value for a and b. It is coming. So in our question we have given the value for a and b also. Okay, a and b are positive real number, so you may take any value for a and any value for b. Okay, so for easy calculation we'll take some easy value. Okay, that can give us easy answers. Okay, so if I consider a 5 b 6, okay, so we'll get the d square plus a is a 5 d plus b is a 6 which is equal to 0. Okay, this is a quadratic equation. Now it is easier to find out the root. Let's check out the root, how the root is coming. So if root is coming from the complex, then we say that our solution, complex solution y of x is equal to c1 cos bx plus c2 sin bx and outer bracket e to the power mx. Okay, this is the solution for complex. If the root is repeated, then we write c1 e to the power m1x plus c2 e to the power m2x as a solution. If the root are distinct, and if root are repeated, then we write c1 plus c2x e to the power mx is the root of our a solution of our roots. Okay, now let's find out which type of the root we are getting here, and then we'll go for the solution of our differential equation. Okay, so d square plus 5d plus 6, I know that you all are able to find out the root of our quadratic equation, which we will get the d plus 3 and d plus 2, which is equal to 0. Okay, these are the root of our equation, so we'll get the d is a negative 3 and d is a negative 2. Okay, so here we can see that roots are distinct, not repeated. So the solution for our differential equation, we write y of x is equal to c1 e to the power m1x plus c2 e to the power m2x. Okay, this is the solution of our differential equation. Now replace m1 here, m2 here. Okay, c1 e to the power minus 3x plus c2 e to the power minus 2x, which is a y of x. Okay, so I got the y of x, c1 e to the power minus 3x, c2 e to the power minus 2x. Okay, now apply the initial boundary condition. Okay, so what we have, y of 0 and y of 1 both are equal. Okay, these two conditions are equal, y of 0 which is equal to y of 1. Okay, so y of 0 which is equal to y of 1, both are equal. Now find out y of 0. So what is y of 0? c1 e to the power 0, which is 1, plus c2 e to the power 0, which is 1. Okay, that means y of 0 will get the c1 plus c2. Okay, how c1 plus c2, instead of x replace 0, this 0, this 0, so e to the power 0 1, e to the power 0 1, so remaining c1 plus c2. Okay, and y of 1, c1 plus e to the power, instead of x it is 1. Okay, so c1 e to the power minus 3 plus c2 e to the power minus 2. Okay, so these are the value y of 0 and y of 1 we have here. Okay, now take term of c1 together, take term of c2 together. Okay, so c1 minus c1. Okay, so c1 common, 1 minus e to the power minus 3, 1 minus e to the power minus 3 plus c2 common, 1 minus e to the power minus 2, which is equal to 0. Okay, so c1 1 minus e to the power minus 3 plus c2 1 minus e to the power minus 2, which is equal to 0. Okay, so I got this equation over here. Now using this, find out the value for a c1 c2 and substitute it into our solution, and let's figure it out how many constants are coming. Okay, so find out the value for c1. What we will get, the c1 which is equal to, take this term other side, minus c2 into 1 minus e to the power minus 2, multiplicand it comes dividend, 1 minus e to the power minus 3. Now put this value for c1 into our solution. Okay, so here we can see that if you're going to substitute c1 here, so this c1 it will get vanishes. If c1 is not there, then this term it will come. Okay, and this term is completely involvement of a c2 term. There is no c1, that means c2 it is here, and this constant term plus c2 here, this constant term. Okay, okay, e to the power 3x, e to the power 3x, so we can write as the c1 this way, this into e to the power minus 3x. Okay, so let me write again here. So here we can see we got the our solution, c2 into this term, e to the power minus 3x into c2 to the power minus 2x. Now here we can see we can write y of x as a linear combination of their basis. Okay, so basis for e to the power minus 3x, this one it is first basis and this one is the second basis. Okay, that means we can write y of x as a spanning set. Okay, the linear combination for basis. Okay, so like for finding the basis from polynomial, I already explained my previous lecture. If you wanted to see understand these things very clear, you may see my videos. Okay, now but let me explain. If I have polynomial p of x as a naught plus a1x plus a2x square plus so on. Okay, if I have this polynomial, so I write their basis as 1, okay, x square and so on. Okay, this is the basis for our polynomial. Okay, and the number of bases in our polynomial, which means dimension of our vector space. Okay, number of bases in our polynomial means which is a dimension of a vector space. Okay, now a naught, a1, a2 are the constants over here, and 1, x square, these are the bases. Now here we can see this is the constant a naught, this is a constant a1. First basis e raised to minus 3x, second basis e raised to minus 2x. Okay, so I got the first basis e raised to minus 3x and second basis e raised to minus 2x. Okay, this is a linear combination. Okay, for these two constant as well as basis. Okay, and the number of bases which present in our solution means which is a dimension of our vector space. Okay, so how many bases are there? First basis and second basis. So number of bases which is a 2. Okay, if a number of bases which is equal to 2, then we say that the dimension of our vector space. So here we have number of constant, it is a C2 only. Okay, not a two different constant, we have single constant. Oh, so constant we have two constant, it is a constant we have C2. Okay, which is a constant over here. Okay, C2 is a constant, but with respect to C2 constant, so with respect to C2, if we take C2 common from here, under bracket it will remain negative of this term into e raised to minus 3x plus e raised to minus 2x. Okay, so we have only one constant with respect to remaining this term. Okay, so this term it is here. So with respect to single constant, we have only one variable, okay, which is a basis. So this is the addition over here for these two terms. Okay, whenever we take C2 common from here. Okay, so let me explain how y of x is coming. Here for your understanding, I written solution over here, then I will explain last two step later. Okay, so here we can see, first of all I consider their differential equation. I found the root, then I found their solution of y of x. By using initial boundary condition, I found the value for C1 which is associated with the C2. I replace the value for C1 over here, C2 kept it same. Now what I have done in the last step, I taken constant C2 out from here. So our polynomial, whenever we have polynomial p of x as a naught plus a1 x plus so on, their basis can be written as 1x x square and so on. Okay, so a naught, a1, a2 are the constant and their coefficient are the basis. Okay, now here we can see that C2 is only constant here. Okay, so if we take that C2 constant common and out from here, we will get this polynomial inside. Only one polynomial with respect to this constant. So we have only one constant over here. So with respect to single constant, we got the only one basis. With respect to single constant, we get the only one basis. Always remember, with respect to one single constant, we'll get the only one basis. Okay, and the number of bases we have here, then this bracket only the one single basis. Okay, since C2 is out there, so number of bases which is only one, and if number of bases is one, then dimension of our V with a set of solution, okay, which is a 1. Okay, dimension of V which is a 1, that is the number of bases in our set which is the dimension of a vector space, or we call it as the dimension of set of solution to our question. Okay, so you may apply some other way to find out the dimension. Okay, dimension of vector space minus number of linearly independent restriction. Okay, so we have only one linearly independent restriction. Okay, that is y of 0 is equal to y of 1, which is only one linearly independent restriction to our polynomial. Okay, and the dimension of a vector space. Okay, how can we find the dimension of vector space? That means that the highest power of our polynomial is the dimension of vector space, and the highest power means double differentiation. So dimension of vector space is a 2, and number of li restriction which is only 1, so 2 minus 1 is 1. Okay, dimension of vector space is a 1 over here. Okay, I hope you all have understood this complete solution. It is very easy calculation for finding the dimension of vector space. Nothing is difficult over here. So let's go for one more example which is also asked in GATE exam. So question it is quite easy over here, that we have to find out the dimension of a C naught upon M. It is a no answer type question. So let's read the question. We have C naught here. C naught such that xn belongs to R and xn tends to 0. All xn we have here, and which is from the real number. Okay, and em also given here. Xn belongs to C naught, x1, x2, x10, which is equal to 10. Okay, and then we want the dimension of a C naught upon M. Okay, so for finding the dimension of any a upon b, c upon d, we write dimension of a minus dimension of b. Okay, which is the number of li restriction. So here a dimension of a C naught upon M, this is the standard result we have to apply over here to get the dimension of a C naught upon M. Okay, so dimension of a C naught keep as it is, and dimension of M. Okay, so how to find the dimension of M? Okay, so dimension of M means we have how many number of restriction, li restriction we have here. So number of li restriction means x1, x2, x10. Okay, their addition is a 10 is a li restriction. That means linearly independent restriction only one we have here. Okay, So if we take only one restriction out from C naught, then we will get the dimension of M. Okay, xn it is from the C naught, xn itself from the C naught, and C naught is the here vector space, xn belongs to R. Okay, and xn from C naught, that means all M we are taking from the C naught. But if we take that restriction out, that means C naught, if we take C naught from restriction from C naught, then we'll get the dimension of M. Okay, dimension of M means if we take that restriction C naught out from C naught, okay, then we get the dimension of M. So dimension of M, I can write this one as number of Li restriction, okay, which is 1. We have only one restriction and we have to take it out from here. So dimension of C naught minus 1, okay, number of restriction we have here only 1, and we have to take that restriction out from C naught, then we will get the dimension of M. Okay, the dimension of M means it is completely free values, okay, restriction from C naught. Okay, and if you wanted to take completely free restriction, so we have to take this out from the M, and if you wanted to take this M from out from M, then remove from the C naught. Okay, so dimension of a C naught minus first only one Li restriction, we get the dimension of M. Okay, I hope you all have understood how can we find the dimension of C naught M. Okay, so dimension of C naught as it is, dimension of M can be written as, so minus keep as it is, dimension of C naught minus 1. Okay, because only one restriction we are taking out from here, then we'll get the dimension of M. Okay, so dimension of C naught it is equal to here dimension of C naught minus dimension of C naught plus 1. Okay, so this one get cancelled, only we are here with the 1. Okay, so I hope you all have understood the dimension of C naught upon M, how we found here. Okay, this is just little confusing question, but not that difficult. Okay, so if you think it properly, try to fill that question, you will get the easy answer. Okay, so dimension of C naught, it will remain same, only the matter is here to find out the dimension of M. Okay, and dimension of M means the value which is a free from C naught, the vector value from our vector space which is a free from C naught, and we do not want C naught over here, so take that dimension of C naught out from our M. Okay, so that means we have only one linearly independent condition. Okay, so take dimension of C naught minus 1, then you will get the dimension of M. Okay, this is our required answer. I hope you all have understood my today's two of these questions from linear algebra previous year question paper. It is very easy question that need to apply some basic concept and conceptual based question is this one. Okay, so thank you everyone, thank you for my today's lecture.